For most people, Earth's magnetic field feels invisible and permanent. Like gravity or air, something that has always existed and never seemed capable of changing in any meaningful way. It quietly protects the planet from solar radiation, keeps satellites functioning, and allows modern technology to work without ever being noticed in daily life. For a long time, scientists believed Earth's magnetic field changed very slowly, over thousands of years, making it irrelevant for human lifetimes. That assumption shaped how satellites were designed, how risks were calculated, and how space missions were planned decades in advance. But when researchers began re-examining old satellite data, they noticed patterns that did not fit this calm and predictable picture. The changes were subtle and gradual, not dramatic enough to cause failures, which made them easy to ignore at the time. Some regions of the magnetic field weakened faster than expected, while others behaved inconsistently across long periods of observation. Individually, these details looked harmless and were often explained away as sensor limitations or normal variation. But when scientists compared data across many satellites and many decades, the inconsistencies began to align in uncomfortable ways. This was not a single error, a broken instrument, or a temporary disturbance caused by the sun. It was persistent behavior that repeated over time and space. The most unsettling part is that this data was never hidden, classified, or newly discovered. It came from satellites that completed their missions years ago and quietly left their measurements behind. At the time, nothing failed, nothing broke, and nothing forced urgent investigation. So the data stayed archived, waiting for better tools and better questions. Science often moves forward without looking back, assuming the past was already understood. But sometimes the past is where the first warnings are buried. And this story begins with realizing that something important may have been changing right in front of us for decades. When scientists compared decades of satellite measurements, one specific region kept appearing again and again as a quiet outlier that refused to behave normally. This area sits above the South Atlantic, stretching between South America and Africa, and it slowly weakened while the rest of the magnetic field stayed relatively stable. At first, this weakening was treated as a local irregularity, something small that did not affect the planet as a whole or demand urgent explanation. But as years passed, the region continued to grow larger and weaker, showing changes that no longer fit simple models of random variation. Satellites passing through this zone experienced higher radiation exposure, occasional system glitches, and increased risk, even though nothing catastrophic happened. Engineers adjusted operations to protect equipment. But the deeper question of why this region existed remained unanswered for a long time. What made scientists uncomfortable was not the existence of one weak spot, but the fact that it kept changing in ways that models failed to predict. Older textbooks described Earth's magnetic field as mostly symmetrical, with slow drift that looked neat and orderly on paper. This region broke that picture completely because it behaved more like a moving scar than a stable feature. When older satellite data was added to newer measurements, it became clear that this was not a recent problem at all. The region had existed for decades, quietly evolving, expanding, and shifting location without drawing public attention. No alarms were triggered because the changes were slow, and slow changes are easy to ignore in both science and daily life. But slow does not mean harmless, especially when systems depend on long-term stability. This raised an uncomfortable possibility that Earth's magnetic field may be more dynamic on human timescales than previously assumed. If one region could behave this way for decades, others might follow patterns we have not recognized yet. And that realization forced scientists to ask a question they were not eager to answer. What if this was not an exception, but an early sign of a larger process we still don't fully understand? One of the main reasons this never became a global warning is that science reacts very differently to slow processes than to sudden disasters that demand immediate attention. There was no single moment when Earth's magnetic field failed dramatically, collapsed suddenly, or caused visible damage that would force urgent public concern. Instead, the changes unfolded quietly over decades, appearing as background variation rather than a clear and urgent signal of danger. Scientists are trained to notice sharp deviations and sudden anomalies, not slow trends that only become meaningful when viewed over long periods of time. Another reason is that the effects were mostly invisible to people on the ground, making them easy to overlook outside scientific circles. Airplanes continued to fly normally. Power grids remained stable, and daily life showed no obvious signs that anything unusual was happening. Most of the real consequences were limited to satellites, instruments, and technical systems operating far above Earth's surface. Engineers handled these issues internally by adjusting satellite operations instead of issuing public warnings or alarming statements. There is also an institutional reason that rarely gets discussed openly, because it challenges how science is funded and organized. Research funding tends to favor new discoveries and exciting results, not long-term reanalysis of old data that creates uncertainty. Slow anomalies raise uncomfortable questions without offering clear answers, which makes them difficult to justify in funding proposals. Another complication is that magnetic field behavior sits between several scientific disciplines at the same time. It is not purely geology, not purely space physics, and not purely atmospheric science, which makes responsibility unclear. When a problem belongs to multiple fields without a clear owner, it often receives less focused attention. Older satellite data came from many different missions using different instruments and measurement standards. Decades ago, comparing those datasets meaningfully was extremely difficult due to technical and computational limits. As a result, the data remained fragmented, stored in archives, and rarely examined as a single continuous story. What changed recently was not fear or urgency, but capability. Modern computing finally allowed scientists to connect decades of measurements into coherent long-term patterns. Once those patterns became visible, ignoring them stopped being the safest option. That is when quiet dismissal slowly turned into quiet concern. Not because disaster was certain, but because old assumptions no longer felt reliable. The moment Earth's magnetic field starts behaving differently, the first systems to feel it are not people, but satellites silently orbiting above the planet. Satellites rely on predictable magnetic conditions to protect electronics from radiation, and even small changes can shorten their lifespan without any obvious warning signs. In weakened regions of the magnetic field, satellites experience higher radiation exposure, which can cause glitches, data corruption, or permanent damage over time. These problems rarely make headlines because engineers quietly adjust operations, turn systems off temporarily, or accept gradual degradation as normal risk. GPS systems are also affected more than most people realize, because signal accuracy depends on stable conditions between satellites and Earth. Small magnetic disturbances can introduce tiny timing errors, and tiny errors matter when systems depend on nanosecond precision. Individually, these effects are manageable, but over time they compound, especially as more infrastructure depends on constant satellite reliability. Modern life is built on invisible systems that assume space behaves the way it did in the past. Communication networks, financial systems, navigation, weather forecasting, and emergency services all rely on satellites working as expected. If Earth's magnetic environment becomes less predictable, those systems require more correction, redundancy, and cost to maintain. Another uncomfortable detail is that satellite problems are often blamed on solar activity rather than Earth's magnetic field itself. Solar storms are dramatic and easy to explain, while slow magnetic changes are subtle and harder to communicate. This means some long-term risks may be misattributed or underestimated because they do not fit simple narratives. The most interesting part is that none of this implies sudden collapse or catastrophe. It implies friction. More maintenance, more failures, higher costs, and systems that quietly become less reliable over time. These are the kinds of problems that rarely cause panic, but slowly reshape how technology works. And because the changes are gradual, society adapts without realizing the environment itself is shifting. This is why scientists care about old satellite data now more than ever. Not because something dramatic is about to happen, but because long-term stability depends on understanding slow changes early. By the time problems become obvious to everyone, options are already limited. Old data does not predict disaster, it predicts adjustment. And adjustment is always easier when you see it coming. When scientists started asking whether Earth's magnetic field changed like this before, they quickly realized the answer was uncomfortable and well documented. The planet's magnetic field has never been perfectly stable, and geological records show it has weakened, shifted, and even flipped many times in the past. Rocks formed millions of years ago preserve magnetic information, acting like a frozen record of how Earth's field behaved at different moments in history. These records reveal periods when the magnetic field weakened significantly without fully collapsing or reversing direction. During those times, Earth was exposed to higher levels of radiation, even though life on the surface continued to survive and adapt. What makes this interesting today is not that such events happened, but how slowly and quietly they unfolded. Some weakening periods lasted thousands of years, with no single dramatic moment that would have warned observers in advance. From the inside, these changes would have felt gradual, subtle, and easy to ignore until their effects accumulated. Scientists now compare those ancient patterns with modern satellite data and notice similarities that raise difficult questions. The comparison does not suggest an imminent catastrophe, but it does suggest the current changes are not unprecedented. This matters because ancient changes happened long before satellites, power grids, and global technology networks existed. Modern civilization depends on systems that are far more sensitive to magnetic conditions than anything in Earth's past. That makes even moderate magnetic changes more disruptive today than they ever were for early life or ancient humans. Another uncomfortable detail is that past weakening events were not uniform across the planet. Some regions were affected much more strongly than others, creating uneven exposure rather than a global disaster. This matches what satellites observe today, where certain areas weaken faster while others remain relatively stable. That similarity is difficult to ignore, even if it does not point to a clear outcome. The past does not predict the future directly, but it provides context that modern data alone cannot offer. And that context suggests Earth's magnetic field is dynamic on timescales that matter to human civilization. Not because the planet is unstable, but because stability was always an assumption, not a guarantee. Understanding that difference changes how scientists interpret everything they are seeing now. When people hear about changes in Earth's magnetic field, many immediately imagine a sudden collapse, disaster, or the end of modern civilization. That reaction is understandable, but it is also misleading. Because magnetic field changes do not work like switches that suddenly turn off. Even during past weakening events, Earth's magnetic field never disappeared completely, and life continued without global extinction. What scientists see today does not suggest an imminent magnetic collapse or a sudden reversal happening within human lifetimes. The real concern is not speed, but unpredictability, because slow systems can still produce serious consequences when technology depends on precision. Modern civilization relies on satellites, timing systems, and electronics that are far more sensitive than anything in Earth's past. That means even moderate changes can have outsized effects, not through destruction, but through increased failure rates and higher maintenance costs. Another important point is that scientists understand the magnetic field better than ever before, even if some details remain unclear. Satellites constantly monitor changes, models are updated regularly, and risks are actively studied rather than ignored. This is not a situation where humanity is blind or unprepared, but one where uncertainty remains higher than people assume. The real shift is psychological rather than catastrophic. For decades, the magnetic field was treated as background infrastructure that did not require active management or concern. Old satellite data challenges that mindset by showing that the environment around Earth is more dynamic than expected. That forces scientists to think differently about long-term planning instead of relying on static assumptions. The most interesting part is that this shift does not lead to panic, but to humility. It reminds us that even well-studied systems can behave in ways that surprise us over long timescales. Space is not an empty void, and Earth's protective systems are not frozen in place. They are active, evolving, and shaped by forces that operate slowly but persistently. Understanding that does not weaken science, it strengthens it. Because preparation is always easier when assumptions are questioned early rather than after systems fail. Old data did not predict disaster. It revealed complexity, and complexity is always more challenging than simple fear. Right now, scientists are not waiting for a dramatic event or sudden failure, but closely tracking slow magnetic changes that only become meaningful when observed over many years. Modern satellites continuously map Earth's magnetic field strength, shape, and movement, creating detailed records that are far more precise than anything available decades ago. Researchers focus on regions where the magnetic field weakens faster than expected, because these areas reveal how the system behaves under long-term stress. Instead of searching for collapse, scientists watch for acceleration, direction changes, and interactions that suggest existing models may be incomplete. One key question is whether weakened regions are growing, merging, or shifting faster than historical averages seen in older satellite records. A small increase in speed does not signal disaster, but it does indicate that assumptions used in long-term planning may need revision. Another major focus is how magnetic weakening interacts with solar activity that was once considered manageable. When Earth's magnetic shield is weaker, solar storms that previously caused minor issues can have stronger effects on satellites and electronics. Scientists also monitor radiation exposure levels in low Earth orbit, where communication, navigation, and observation systems are densely concentrated. This matters because future plans involve placing even more infrastructure and long-duration missions in these environments. What separates today from the past is not fear, but context and continuity. Decades ago, data existed in fragments, scattered across missions and reports without a clear long-term picture. Today, those fragments form a continuous timeline that allows scientists to see slow trends as they unfold. Another important change is transparency, because magnetic field data is now shared globally and analyzed by independent teams. This reduces the chance that gradual changes are dismissed simply because they do not look dramatic. The most interesting part is that nothing alarming is happening right now. And that calm is exactly why scientists are paying attention. Slow systems only reveal their behavior to those who watch patiently. We are living inside one of those systems right now. And understanding it depends not on panic, but on paying attention before change becomes obvious to everyone. Old satellite data did not suddenly reveal danger or predict disaster, but it quietly forced scientists to rethink how stable Earth's environment really is over human timescales. For a long time, the future was planned as if space and Earth's protective systems would behave tomorrow exactly as they behaved yesterday. That assumption made progress easier, because it allowed engineers and planners to focus on technology instead of environmental uncertainty. Old data challenged that comfort by showing that slow systems still change in ways that matter when infrastructure depends on precision. The most important shift was not scientific, but philosophical, because it changed how researchers think about risk. Instead of asking whether something will fail suddenly, scientists now ask how small changes accumulate over long periods without being noticed. This mindset applies not only to the magnetic field, but to many systems humans depend on without questioning. Old data reminds us that stability is not the absence of change, but the ability to adapt before change becomes disruptive. Future missions to the Moon, Mars, and beyond are now planned with greater attention to environmental uncertainty. Designs include more redundancy, more monitoring, and more flexibility to respond to slow but persistent shifts. This does not slow exploration, but it changes its character from confidence to caution. Caution is often mistaken for fear, but in science, it is a sign of maturity. The most unsettling realization is that nothing dramatic forced this change in thinking. No collapse happened, no warning arrived, and no deadline was announced. The future shifted quietly, driven by data that waited decades to be understood. That is why revisiting old measurements matters more than chasing constant novelty. New discoveries excite us, but old data teaches patience. It shows how easy it is to miss important changes when progress moves faster than understanding. The universe does not need to surprise us with sudden events to change our plans. Sometimes it changes them slowly, through numbers that refuse to stay silent. And the real lesson of old NASA data is not about fear or failure. It is about listening carefully, even when nothing seems urgent, because the future is often shaped long before anyone realizes it has already begun. One reason slow changes are dangerous is that they rarely trigger alarms, because human systems are designed to react to sudden failures, not gradual shifts. We notice explosions, crashes, and outages, but we struggle to notice trends that move just slightly out of alignment each year. Earth's magnetic field changes fit perfectly into this blind spot, because they do not break anything immediately or demand urgent response. Instead, they add friction to systems that were designed under assumptions of stability that no longer fully apply. This kind of risk is hard to communicate, because it sounds abstract and distant compared to visible disasters. People ask what will happen and when, but slow systems do not offer clear dates or dramatic moments. They only offer increased probability of failure, higher costs, and reduced margins over time. That makes preparation less exciting and prevention harder to justify, even when evidence quietly accumulates. Old satellite data forces scientists to confront this problem honestly, without the comfort of clear deadlines. It shows that some of the most important changes are already underway before anyone feels affected by them. By the time effects become obvious to the public, options are usually fewer and more expensive. This pattern appears again and again in science, engineering, and history, not because people are careless, but because attention is limited. The lesson is not that catastrophe is coming, but that awareness must arrive earlier than urgency. Earth's magnetic field is not a threat waiting to strike, but a system reminding us how easily assumptions become habits. Habits work until they don't, and when they fail, the cause often feels sudden, even if it was building for decades. Old data gives us a rare advantage, because it shows change while there is still time to adapt calmly. That is why scientists keep returning to it, even when nothing dramatic seems to be happening. Because the most dangerous moment is not when something breaks. It is when change is still quiet enough to ignore. And understanding that difference may be one of the most important skills humanity needs as it plans a future beyond Earth. Old satellite data shows that humans often mistake stability for permanence, especially when changes happen slowly and do not create immediate problems or visible failures. Systems can shift for decades without breaking, quietly accumulating stress until adaptation becomes harder and more expensive than anyone expected. This story is not about disaster or collapse, but about how the universe records change silently through data long before consequences appear. Old measurements do not predict fear, they reveal responsibility, because understanding arrives earlier than urgency if someone chooses to look back. The real question is not what will happen next, but whether humanity learns to listen while change is still quiet and manageable.